For the last 2 days, the Chang'e 6 space probe has been collecting these precious rock and soil samples.
We always see the same face of the moon from Earth. The far side stays hidden, older, rougher, and more mysterious. China's Chang'e 6 mission landed there.
This is a significant mission because it provides a lot of scientific value, figure out more about the geology and the composition of the South Pole, which is an area on the moon.
Collected samples and brought them back to Earth. Let's see what those rocks are telling scientists about the moon's secret history. Why the far side looks so strange. If you have ever looked up at the moon and wondered what hides on the half we never see, you are not alone. For most of human history, that hidden face was one of the biggest mysteries in the sky. The moon keeps the same side turned toward us because it is tidally locked to Earth. So every night we stare at the same set of familiar features. That makes the far side feel almost like a secret chapter that was glued shut until technology finally peeled it open. Over the years, several spacecraft have sent back photos that have made people realize something surprising. The far side does not look anything like the smooth patterns we see on the near side. It is rougher, more chaotic, and full of deep scars. It almost feels like two separate worlds stitched together. To understand why, it helps to go back to the moon's early days when everything was extreme and nothing looked peaceful. The moon formed after a massive collision between the young Earth and a Mars-sized body more than 4 billion years ago. The violence of that impact created huge clouds of molten debris that eventually came together and turned into the moon. Once it settled into orbit around Earth, gravity locked its rotation so the same face stayed pointed at us. From that moment on, the far side became the hidden side of the story. The most obvious difference between the two sides is the way they look. The near side is covered with dark patches known as Maria. These are the ancient lava plains that give the moon its patterns. If you have ever looked at the moon and traced shapes in those dark regions, that is what you are seeing. But on the far side, those smooth plains are almost missing. Lava barely made it to the surface there. Instead, the far side has a thicker crust that acted like a barrier. This thicker crust may have come from the slow merging of an early companion moon that crashed into the far side long ago. Whatever the cause, that extra thickness kept molten material trapped beneath the surface. Because of this, the far side is dominated by craters. They sit inside other craters and stretch across the landscape in a jumbled pattern. The biggest of them all is the South Pole Aitken Basin. It is one of the largest impact basins in the entire solar system and reaches around 13 kilometers deep. It is so wide that it would take hours to fly from one end to the other. This basin alone tells a story of tremendous impacts that shaped the moon's far hemisphere. When scientists first saw photos from the Luna 3 mission in 1959, they realized that the far side was almost like the moon's own rugged wilderness. Those first images were grainy, but they were enough to show that the hidden half looked nothing like the side everyone knew. The Apollo astronauts later confirmed this when they orbited the moon. While 2 astronauts walked on the surface, 1 astronaut stayed in the capsule and got a direct view of the far side. Their photos revealed steep hills, jagged terrain, and an incredibly cratered landscape. Many viewers have wondered if the far side is dark all the time. The idea shows up in music and pop culture and has become part of the way people talk about the moon. In reality, the far side receives the same amount of sunlight as the near side. When the near side looks dark to us during a new moon, the far side is fully lit. The only truly dark places are the bottoms of a few deep polar craters where sunlight never reaches. With everything combined, the picture becomes clear. The far side looks strange because it had a different history, a different crust, a different level of volcanism, and probably a different internal temperature pattern. Each of these shaped its landscape in a unique way. We only discovered this recently, but the moon has been holding on to the secret since the beginning of time, and nowhere reveals that history more dramatically than the South Pole Aitken Basin. The South Pole Aitken Basin Landing. On the 3rd of May 2024, the Chang'e 6 spacecraft lifted off from the Wenchang launch site in Hainan. It was heading for the hidden hemisphere, to a smooth patch of dark lava inside the ancient Apollo crater, which lies within the even larger South Pole Aitken Basin. This basin stretches about 2,500 kilometers across and plunges up to 13 kilometers deep. It is one of the biggest impact structures in the entire solar system, and it has been sitting there for more than 4 billion years, packed with clues about the moon's violent past. Reaching the far side is not as simple as just pointing a rocket at the moon. Because that side never faces Earth, radio signals cannot reach a lander directly. China solved this by placing a relay satellite, Queqiao-2, out in deep space behind the moon. Think of it as a floating Wi-Fi repeater that listens to the lander and then passes the message back to Earth. Without this quiet middleman, Chang'e 6 would have landed in total radio silence. After several days in lunar orbit, the landing drama began. The lander separated from the main spacecraft and started its descent toward the South Pole Aitken Basin. The surface below is full of craters, boulders, and slopes that could easily tip a lander over, so the mission relied heavily on automation. Cameras scanned the ground, and an onboard computer searched for safe patches, comparing brightness and shadows to avoid big rocks and steep edges. At about 100 meters above the surface, the lander paused and hovered. A laser 3D scanner swept the area, building a quick map of the terrain right under its belly. Only once the system was satisfied did Chang'e 6 begin a slow, straight drop toward the selected landing spot. It finally touched down in the southern part of the Apollo Basin on the 2nd of June 2024, around 6:23 Beijing time. In the Beijing Flight Control Room, engineers watched their screens shift from abstract data to the simple confirmation that every space team dreams of, a safe landing. Applause broke out, and China had just pulled off a second successful landing on the far side. Landing was only the first half of the story. The real treasure was in the ground. The plan was to collect around 2 kilograms of lunar soil and rock. For up to 3 days, the lander used a drill to grab material from beneath the surface and a scoop to collect loose soil from the top. The site was chosen very carefully. Because the South Pole Aitken Basin is so deep, impacts there may have dredged up material from the moon's mantle, the layer beneath the crust. That means some of the grains and pebbles entering the sample box could have started life dozens of kilometers below the surface. Scientists like Professor John Pernod Fisher and many others have been eager to get their hands on far-side material. Almost everything humans have studied so far came from the near side, from the Apollo missions, the Soviet Luna missions, and China's own Chang'e 5, which in 2020 returned 1.7 kilograms of volcanic rock from Oceanus Procellarum. Those samples were already a big deal. Chang'e 6 goes one step further by sampling a totally different environment, inside the oldest impact basin we know on the moon. Once the collection was complete, the drama moved back to space. The small ascent vehicle on top of the lander fired its engine, lifted off from the far side, and climbed back into lunar orbit, carrying the sealed sample container. There it met up with the orbiter module, transferred the container, and the orbiter began the long trip back to Earth. Weeks later, the return capsule plummeted through our atmosphere and landed in Inner Mongolia, with nearly 2 kilograms of far-side material tucked inside. Those dusty-looking rocks are surprisingly powerful. By measuring their chemistry and age, scientists have confirmed that the South Pole Aitken Basin formed about 4.25 billion years ago. That makes it the oldest and largest impact crater on the moon, and a key marker in the timeline of the entire solar system. The samples also show that the basalts in this region erupted about 2.8 billion years ago, and that the mantle beneath the far side is cooler and poorer in certain heat-producing elements and water than the mantle under the near side. All of this means Chang'e 6 was not just a flag-planting moment for China. It turned the South Pole Aitken Basin from a distant scar into a well-dated, well-sampled laboratory. Now, once those samples reached Earth, they began revealing answers far stranger than expected. If you enjoy space stories that go beyond launch footage and focus on the science, hit subscribe and leave a moon emoji in the comments. It lets me know you want more deep dive space episodes. First clues from samples. When the Chang'e 6 capsule landed back on Earth with nearly 2 kilograms of lunar soil, nobody expected the samples to start rewriting the moon's story this quickly. These tiny grains were taken from a lava plain inside the Apollo crater on the far side, a place nobody had ever touched before. The mix looks ordinary at first glance, just gray dust and dark chips. But once scientists cracked open the containers and began sorting through each particle, they realized they were holding a miniature library of everything that shaped the moon's hidden hemisphere. Each grain carries a clue, and together they build a picture that is far more complicated, far more surprising, and far more interesting than anyone predicted. The first basic question scientists asked was simple. What exactly did China bring back? The answer turned out to be a blend that reflects a long and messy geological life. There is fine regolith, the loose soil formed by billions of years of micrometeorite hits. There are dark pieces of mare basalt that came from old lava flows. There are bright fragments from the ancient highland crust. And then there are the mixed bits, the glassy particles, the welded chunks, and the broken melt droplets created in violent impacts. Even before going into chemistry, the variety alone gives away a crucial fact. The landing site is not a simple place. It is a thin sheet of lava laid over older farside crust, and the soil on top is heavily mixed with ejecta from the Apollo impact that punched a huge hole in the region. You end up with a surface that records both ancient volcanism and deep crustal excavation in one handful. Then came the temperature clues locked inside the basalt crystals. Scientists studied minerals that keep a memory of the heat they formed in, and the Chang'e 6 basalts sat at around 1100 degrees Celsius when they crystallized. That is cooler than similar young basalts collected from the near side, which form closer to 1200 degrees. A difference of 100 degrees does not sound dramatic until you realize it reflects the thermal state of the mantle. The only way the far side magma could be cooler is if the mantle under that hemisphere has fewer heat-producing elements such as uranium, thorium, and potassium. These elements release heat very slowly inside a planet. If the far side mantle is poorer in them, it means the interior has stayed cooler for billions of years. And that cooler interior connects directly to why the far side never developed the wide, smooth volcanic plains that make the near side so recognizable. The chemistry also delivered a surprise about creep, the group of elements that many scientists once believed helped fuel late volcanism on the moon. For years, the idea was that these heat-rich materials pooled under the crust and acted like a booster for magma production. Yet when researchers examined Chang'e 6 basalts, they found almost no sign of creep at all. These rocks came from a mantle source depleted in incompatible elements, including the ones normally associated with heating. Now, when you put that next to the Chang'e 5 samples from the near side, which were also unexpectedly low in creep, the story shifts. It turns out that the moon did not rely on that ingredient to keep erupting. The far side proves that lava can still reach the surface even when the usual chemical fuel is missing. Something else must be keeping pockets of the mantle warm enough to melt, perhaps long-lived heat left from the moon's early history, combined with crustal structures that allow some places to rise to the right temperature. One of the most talked about results comes from the water content. A team studied more than 500 soil grains and discovered that the far side location is much drier than many near-side mare regions. The measurements came in below 1.5 micrograms of water per gram of soil. Near-side samples range from 1 to 200 micrograms. That is a huge gap. And it tells us that the far side mantle and crust at this location may be naturally low in volatile elements. It might also reflect how impacts, crust thickness, and the general environment control the amount of water that can be implanted by the solar wind. The Chang'e 6 site is not one of the permanently shadowed polar craters where water ice might hide, so this finding does not contradict the search for ice. It simply means that ordinary far side mare regions are not as water-rich as their near-side cousins. This matters for future exploration because it shapes how we think about resources, past volcanism, and the distribution of volatiles across the moon. The samples also captured evidence of a complicated impact history. Some basalt fragments show shock marks, pressure deformation, and melt veins created by later collisions. When you combine that with the soil's strong contribution from neritic highland crust, you get a picture of a surface repeatedly churned by impacts. The thin lava sheet was broken, mixed and stirred with deep crustal material from the Apollo and South Pole Aitken structures. The regolith becomes a blended timeline, merging volcanic activity with major impact events into one compact archive. It is a messy history, but through that mess, you can read how the farside crust was reshaped again and again. Another completely new insight comes from tiny magnetic signatures trapped in the basalt. These signatures act like a fossil record of the moon's ancient magnetic field. Researchers found that around 2.8 billion years ago, the magnetic field was not fading smoothly, the way many models suggested. It actually strengthened again for a period of time. This is the first magnetic record ever taken from the far side, and it fills a long gap in our understanding of how the lunar dynamo behaved. It also links directly to the age of the basalts themselves, showing that volcanism and the internal magnetic engine were still interacting deep into lunar history. Small stones that look ordinary on the outside now tell us that the moon's core and mantle were more dynamic and more unpredictable than we thought. Put all this together and a very clear picture forms. The far side mantle is cooler and more chemically depleted than the near side, yet still able to generate pockets of magma. The soil is a blend of thin basalt over ancient highland crust, mixed with ejecta from one of the biggest impact structures in the solar system. The region is drier, the volcanic source lacks the usual heating elements, and the rocks carry a magnetic memory that reshapes our understanding of the lunar core. And the most exciting part is that these results come from only a small portion of the samples. More labs around the world are still waiting for their allocations. Every grain that passes under a microscope has the potential to shift another piece of the story. Chang'e 6 has taken the far side from a place we could only imagine to a place we can finally study directly. For the first time in history, the hidden hemisphere is not just a blurry photo or a distant landscape. It is something scientists can hold, test, and compare grain by grain to the side we have known for decades. These clues don't just rewrite lunar history, they reshape our understanding of Earth's beginnings as well. Why this matters for Earth's story? When viewed in the broader context, the Chang'e 6 samples are revealing much more than what the moon's far side looks like. They are unlocking new details about the early Earth-Moon story, a story that shaped our tides, rotation, climate, and even the environment where life first began. The moon isn't just a satellite, it is a preserved record of how our planet evolved. And these new samples give scientists another vital piece of a puzzle they have been reconstructing for decades. The leading theory for the moon's origin is the giant impact model. In this scenario, a Mars-sized body collided with the young Earth over 4 billion years ago, scattering molten debris into orbit. That material eventually clumped together and cooled into the moon. After the impact, Earth spun much faster, with days lasting only a few hours, and the moon orbited much closer. This model fits because lunar rocks, both from Apollo and previous Chinese missions, share isotopic fingerprints with Earth. They also preserve evidence of a global magma ocean that gradually solidified. Chang'e 6 extends that story by adding a farside chapter. The basalts and crust fragments show that the moon cooled unevenly, giving its near side and far side different temperatures, chemistries, and internal structures. That uneven cooling plays a critical role in how the moon responds to Earth's tides. When Earth's gravity pulls on the moon, it causes the lunar interior to flex slightly. The strength of that flexing depends on temperature and mineral composition. These properties determine how much tidal energy the moon absorbs and how quickly it drifts away from Earth. Today, laser reflectors show the moon receding at a few centimeters per year, while Earth's rotation slows, adding milliseconds to each day over centuries. Ancient tidal patterns preserved in rocks reveal that Earth's days were shorter and years contained more days in the distant past. To tie this together, scientists build Earth-Moon models that factor in both bodies' internal structures. NASA's Grail mission showed the near-side mantle is warmer and softer than the far side. Chang'e 6 supports this by confirming the far side mantle is cooler and poorer in heat-producing elements. Feeding these findings into tidal models refines how fast the moon drifted outward over time, giving a clearer view of the tidal environment on early Earth, when microbial life was emerging. During that period, the moon was much closer and tides were stronger, frequently stirring nutrients and driving wet-dry cycles that could have encouraged early biochemistry. The moon also stabilizes Earth's axial tilt, which governs our seasons. Without it, Earth's tilt would vary chaotically. The moon's gravitational influence keeps the tilt steady, maintaining climate stability that supports life. To know if early Earth had similar stability, researchers need to understand how angular momentum shifted between Earth and the moon, a process dependent on tidal dissipation. The cooler far side mantle revealed by Chang'e 6 refines estimates of how much energy the moon absorbed, improving models of long-term climate stability. Finally, the samples also preserve the shared impact history of Earth and the moon. The South Pole Aitken Basin, where Chang'e 6 landed, was created by a massive collision over 4 billion years ago. Earth endured similar impacts, but tectonics and erosion erased most traces. The moon, lacking these processes, kept its scars, giving scientists a pristine record of early bombardment. By comparing the ages of these far-side rocks with known events on Earth, researchers can better estimate how often our planet was struck and how those impacts influence the oceans and atmosphere where life was forming. In revealing a cooler far-side mantle, prolonged volcanism in a dry environment, Chang'e 6's findings reach far beyond lunar science. They fine-tune our models of ancient tides, rotation, and climate stability, bringing us closer to understanding the world that first hosted life. The moon still holds chapters of Earth's history that vanished from our own rocks, and each new sample helps bring that lost story back into focus. And as we uncover that past, the next step is deciding what to build there. What comes next? On the far side. Over the next few decades, the far side of the moon is going to feel very different from the quiet, mysterious place you see in old space documentaries. Chang'e 4 and Chang'e 6 already showed that you can land there, drive a rover around, and even grab rocks, all while hiding behind the moon with no direct line of sight to Earth. That alone used to sound impossible. Now space agencies are planning something bigger. The idea is to turn that remote, radio-silent landscape into a long-term base for listening to the universe and studying the moon from the inside out. We are moving from quick touch-and-go visits to building a real observing setup that could run for years. One of the first big steps is a mission called LUCY-NIGHT, short for Lunar Surface Electromagnetics Experiment Night. It is a small, low-frequency radio telescope that NASA and the U.S. Department of Energy are sending on a commercial lander to the far side. Picture 4 long antennas folded up for the trip, then slowly deployed on the surface once the lander settles in. LUCY-NIGHT is built to survive the deep cold of the 2-week lunar night and to listen at radio frequencies that Earth simply cannot use. That side of the moon blocks out our mobile phones, radar, and FM stations, so the background there is incredibly quiet. In that silence, LUCY-NIGHT will try to detect faint signals from hydrogen gas in the early universe, from a time before the first stars were born. If it can work through the long nights and send back clean data through a relay satellite, it will prove that precision cosmology from the far side is not just a dream. Engineers are already thinking about what comes after that first Pathfinder. Concepts like Farside imagine a huge swarm of simple antennas spread over tens of kilometers of lunar soil, all linked together into a single giant low-frequency radio telescope. Another idea, the Lunar Crater Radio Telescope, would stretch a fine wire mesh across the inside of a natural crater to create a dish larger than anything on Earth. None of these giant observatories is fully funded yet, but the designs are detailed, and LUCY-NIGHT is meant to show that the basic approach is sound. On the other side of the world, China has its own plans. The International Lunar Research Station, led by China and Russia, aims to build a long-term base in the South Polar region, with robots first and crews later. Chinese scientists have already floated proposals for a massive far-side radio telescope tied into that future base, once heavy cargo landings and power systems are in place. Missions like Chang'e 7 and Chang'e 8 are set to scout the South Pole and test ways to use local resources, all supported by the Queqiao 2 relay satellite that keeps the far side connected. While all that is happening on the surface, another kind of listening is getting ready to start. NASA's Farside Seismic Suite will place 2 sensitive seismometers in Schrödinger Basin, carried by a commercial lander. These instruments will feel tiny moonquakes and distant impacts, giving scientists the first direct seismic record from the far side. When those data are combined with future heat flow measurements and magnetic readings, they will help map the moon's core, mantle, and crust in 3 dimensions in a way we have never had before. If you put all these pieces together, you can start to picture a future far-side science park. In one area, a low-frequency radio array listens quietly to the early universe and to nearby planetary systems. Not far away, a cluster of seismometers and other instruments keeps track of every shake and shiver inside the moon. Relay satellites handle the communication, while strict rules keep the region radio quiet so the telescopes can do their work. The same things that once made the far side feel unreachable, like the lack of direct radio contact in its deep basins, now look like its biggest strengths. Step by step, that hidden hemisphere is turning into one of the most valuable natural laboratories humanity has ever had. So the moon's hidden hemisphere is quietly turning into the next giant leap for science, and we're watching it happen in real time. What discovery from the far side will change our view of the universe next? Stay curious, follow the mission updates, and subscribe for more deep space stories.